Let us look at how we can map magnetic lines of force due to a bar magnet.
Let us take a bar magnet and place it at the center of sheet such that its north pole points towards the north pole of the earth. In this position, the axial line will be parallel to the magnetic meridian. Now let us place the compass at different points on the right side of the bar magnet, north and south, and starting from north pole, mark the points corresponding to north and south poles of the compass needle. Thus, we draw the magnetic line of force. Let us repeat the procedure on the left side of the bar magnet. Once we have mapped this magnetic field, you get magnetic lines of force leaving north pole and entering through south pole of the bar magnet.
We also know that at every point the magnetic field due to the earth has a certain value for its horizontal component. Let us represent this component by B0. So in the laboratory, it is this horizontal component due to the earth's magnetic field that influences the magnetic field induction B due to a bar magnet. Remember that we ignore B0 only when B is very large compared to B0, that is close to a bar magnet. Now, according to inverse square law, B decreases with distance while B0 remains constant both in magnitude and direction at a given place. The direction is a line passing through the magnetic meridian, that is, the line joining magnetic north and south poles of the earth. Thus, at any point near a bar magnet, the magnetic lines represent the resultant effect of B and B0. Therefore, there are some points around the bar magnet where B and B0 are equal in magnitude and opposite in direction. These points at which B and B0 cancel each other so that the resultant magnetic field is zero are called neutral points.
A point where the magnetic field induction B due to a bar magnet is equal in magnitude and opposite in direction to the horizontal component of Earth's magnetic field induction B0 is called a neutral point, or a point at which the magnetic field induction B0 due to a bar magnet is nullified by the horizontal component of Earth's magnetic field induction is called a neutral point for the combined or resultant magnetic field. At a point N1 on the right side at a distance d from the center O of the magnet, you will observe that the magnetic needle in the compass does not show any specific direction. It sets itself in an arbitrary direction at N1. Similar behavior will be observed on the left side of N2 at the same distance d. This indicates that at N1 or N2, the resultant magnetic field is zero. Hence, N1 and N2 are the neutral points of the bar magnet. These N1 and N2 fall on the equatorial line of the bar magnet where B is equal to B0 as shown here by the symbol X. When north pole of a bar magnet points towards geographical north pole of the earth, the two neutral points lie on the equatorial line of the bar magnet such that they are equidistant from the center of the magnet. Now let us place south pole of the bar magnet pointing towards the north pole of the earth. Let us repeat the procedure to map magnetic lines. You will observe that at point N1 on top of the S pole, that is south pole of the bar magnet, which is at a distance d from the center O, the magnetic needle does not show any specific direction. Similarly, at point N2 below north pole at a distance d from the center O, the magnetic needle does not point to any specific direction. Thus, the points N1 and N2 are our neutral or null points. These neutral points lie on the axial line of the bar magnet as shown by the symbol X. When south pole of a bar magnet points towards the geographical north pole of the earth, the two neutral points lie on the axial line of the bar magnet such that they are equidistant from the center of the magnet.
We will now calculate the magnetic moment of a bar magnet. For this, we use the information that we get by locating the neutral points of a given magnet.
We know that at a neutral point, the magnetic field due to a bar magnet B is equal and opposite to the horizontal component of Earth's magnetic field induction B0. If we know the value of B0 at a place, we can calculate magnetic moment M and hence pole strength M of a bar magnet. In Andhra Pradesh state, value of B0 is about 0.39 into 10 to the power minus 4 Tesla. Now let us consider the case when the neutral points are on the equatorial line of a bar magnet at a distance d from the center of the magnet. We already know that the magnetic induction along equatorial line B is equal to mu 0 by 4 pi m by d cube. Since B is equal to B0 and B0 is equal to 0.39 multiplied by 10 to the power minus 4 Tesla, we have mu 0 by 4 pi m by d cube is equal to 0.39 multiplied by 10 to the power minus 4. Since mu 0 by 4 pi is equal to 10 to the power minus 7, we have m is equal to 0.39 multiplied by 10 to the power minus 4 multiplied by 10 to the power 7 d cube, or m is equal to 390 d cube am square, which is equation 18. Knowing the value of d from the experiment, m can be calculated. If 2L is the length of the bar magnet, the pole strength m can be calculated from m is equal to m by 2L, which is equal to 390 multiplied by d cube by 2L am, which is equation 19. We now consider the case when the neutral points are on the axial line of a bar magnet at a distance d from its center. As we already know, magnetic field induction along axial line B is equal to mu 0 by 4 pi to m by d cube. At the neutral point, B is equal to B0 or 10 to the power minus 7 2m d cube is equal to 0.39 multiplied by 10 to the power minus 4, or m is equal to 195 d cube am square, which is equation 20. Since d value is known from the experiment, m can be calculated. Hence, the pole strength is m is equal to m by 2L is equal to 195 d cube by 2L am, which is equation 21, where 2L is the length of the bar magnet.
Let us now summarize what we have learnt. A point where the magnetic field induction B due to a bar magnet is equal in magnitude and opposite in direction to the horizontal component of the Earth's magnetic field induction, or B0, is called a neutral point. When the north pole of a bar magnet points towards the north pole of the Earth, the two neutral points lie on the equatorial line of the bar magnet such that they are equidistant from the center of the magnet. When the south pole of a bar magnet points towards the geographical north pole of the Earth, the two neutral points lie on the axial line of the bar magnet such that they are equidistant from the center of the magnet. When neutral points are at a point on the equatorial line of a bar magnet, the relation between the magnetic moment of the magnet and the distance of the neutral point is m is equals to 390 d cube ampere meter square. When the neutral points are at a point on the axial line of the bar magnet, the relation between the magnetic moment of the magnet and the distance of the neutral point is m is equals to 195 d cube ampere meter square.